Hello virtual students. This time it's beryllium chloride, and this is still an exception to the octet rule. Again, we will start by reading the chemical formula, beryllium chloride. So the first step is to write beryllium. It is a group 2 element, so we place here the two dots to represent the two valence electrons, the electrons that participate in bonding. And then Cl subscript 2, that means there are two chlorine atoms. And chlorine is a group 7 element, so 7 valence electrons, the electrons that participate in bonding. Let's write the orbital notation for beryllium. So you can see here two electrons outside in level 2 participates in bonding. 1s2 represented by this one, helium. It is an inner electron, so it doesn't participate in bonding. This is the orbital notation for chlorine. So the orbital notation for neon plus this. So in its outer energy level 3, there are 7 electrons that participate in bonding. These orbitals paired. This one is unpaired. In order to be stable, it will take an extra electron, either by taking it from a metal or sharing it with another non-metal. Now, beryllium chloride forms a molecule. So there's one atom that binds it together. That is what we call the central atom. So in choosing a central atom, we base it on the electronegativity of these elements. This is the electronegativity of each. For beryllium, it's 1.5. For chlorine, it's 3.0. The one with the lower electronegativity is chosen as the central atom. Now, beryllium chloride is a molecule. It's not an ionic compound. The difference in electronegativity is not that high, 1.5, although it will have its ionic properties as well. But it is a molecule. Alright, so next, propose a Lewis dot structure. So beryllium is the central element. Place it at the center. Place the two at the side. Now let's fix this drawing. Now we can propose, this is just a proposal of Lewis dot structure. So let's try to connect this beryllium to this chlorine, this beryllium to the other chlorine by using a single bond. Okay, so single bond. Is this correct? Because as you can see here, chlorine is fine with 8 electrons. So based on the orbital notation shown earlier, chlorine will now have this to fill the last orbital. While beryllium, it won't be able to fill all of the orbitals in level 2. Alright? So 8 electrons for each of these chlorine. So here, let's place the drawing here. Once again, I said that this is an exception to the octet rule. So I'll show you a structure that follows the octet rule for all of this, for beryllium as well. And I'll show you a proof as to why it is not followed here. It is not stable. So the basis of that is the formal charge calculation. So first, let's compute the formal charges of each of these elements for this drawing, for this proposed Lewis dot structure. First of all, the formula for formal charge is the group number minus the summation of bonds plus unshared electron. So if there's a double bond here, it is counted as 1, 2. Alright. Next is, so if this confuses you, this one is an easier representation. So group 7, okay, so group number minus the number of lines and dots associated with it. So I'll show you how it is done. We'll focus on the central element. Beryllium is a group 2 element, and based on this drawing, this formal charge calculation is based on this drawing first. There's 2 lines associated with this beryllium, and there's no electrons here surrounding it. So 0, no dots associated with it, only lines. 0. For this chlorine is a group 7 element based on the periodic table. And there's 1 line associated with this chlorine, and 6 dots unshared. So this is a lone pair. Although it is a lone pair, it is not shared with any. So it is a pair, but it's not shared with any other atom. So that is counted as 6. So the value for this is 0. It's the same, symmetric, 0 as well. Now, the charge here is 0. You take the sum of this, 0, and that is the charge of this molecule, 0. Now let's try a different proposed Lewis dot structure. This one. So you can see if you move this lone pair here, move it here, so that this chlorine, this pair will be shared with our central element. Do it also to the other chlorine. Share it with beryllium. So it will turn out, it will look like this. In this drawing, chlorine has 8 electrons. Chlorine on the left side. Chlorine on the right side also has 8 electrons. Our central element will now have 8 electrons. So all of this will satisfy the octet rule if we strictly follow it. Now let's compute the formal charge for this structure. Beryllium, group 2 element. In this drawing, 4 lines associated with it. So 2 minus 4, negative 2. Chlorine, group 7 element, 2 lines associated with it. 1, 2, 3, 4, 4 dots plus 1. Since this is symmetric, the other chlorine it has the same, computation in terms of formal charge. Group 7, 2 lines, 4 dots plus 1. So you take the sum of this, negative 2 plus 1 plus 1, 0. So it supports the fact that this is a molecule. It has no charge. It's not an ion. It's not a polyatomic ion. Now, this is unstable. First of all, beryllium has a lower electronegativity. It's least electronegative compared to chlorine, and it has a negative charge. If there are charge for each of this, watch my other videos wherein there are charges, it should be that the electronegative element has the negative formal charge. So the least electronegative element shouldn't have a negative formal charge. And not only that, okay, not only that, it should be the best structure is one that is each component has formal charge near 0. Again, the best structure is one that has formal charge for each element near 0. So this one, okay, compared to this, is not that stable. So we'll choose this formal charge computation, and this is based on this structure. So this structure is more stable compared to this one. And in fact, beryllium chloride has this configuration. Single bond with each chlorine. Next is getting the electron group. If you have a single bond, double bond, lone pair, it is counted as 1. So if you have here, from the previous drawing, the double bond, it is counted as one count. It is counted as 1 electron group. Okay, 1 electron group. So suppose, let's say this chlorine is our central element. The lone pair here is also counted as 1. So this electron group or steric number, this counting, affects the geometry of the molecule, how it is arranged in space, how the atoms that composes that molecule is arranged in space. So that is the significance of electron groups. So the steric number or electron group for beryllium chloride with this Lewis dot structure is 2, because there are 2 single bonds. Now, this time I won't show a table about valence shell electron pair repulsion theory table like that. This is simple to analyze. Electrons are negatively charged. So since they have the same charge and they form these bonds, they repel. So the best geometry, the best configuration to minimize that repulsion is that of a linear configuration. So these electron groups will arrange in space in such that they are 180 degrees apart. Because if they are not 180 degrees, let's say 170, 90, they will eventually push each other away and then minimize the repulsion, because if it's near, if it's bent, then there's going to be repulsion because they're near compared to this 180 degree drawing here. So there are 2 electron groups and the electronic geometry is linear. So this electronic geometry is based on how the electron groups are separated. The next is molecular geometry. How are the atoms separated? The atoms that are bonded to the central atom. So it's just the same for this example. Electronic geometry, the electron groups are 180 apart. Molecular geometry, the atoms bonded to the central atom is 180 degrees apart. So both are linear. So this talks about the arrangement. Now let's focus on how bonding occurs for beryllium chloride. So if you check chemistry books, a linear molecular geometry is said to be sp hybridized for the central element. What is the meaning of sp hybridized? There you go. This is again the orbital notation shown earlier, the orbital notation for beryllium. So this is about the central atom. Sp hybridized means that in order to bond, in order to accommodate this bonding with these two chlorine atoms, it has to use one s orbital and then one p orbital. So that means this electron will jump here in order to have two half-filled orbitals, and then the one that will fill it is the electrons from chlorine. So these two will form sigma bonds. Sigma bond here, sigma bond there. So sp hybridized, the orbitals of the central element will hybridize in order to accommodate, will try to accommodate bonding with the two atoms that it bonds with. Okay, so sp hybridized. So there you go. So if you learned something in this video, if this helped you in your homework, preparation for exams, and just to understand how this thing goes, please subscribe to my channel.